Hi everyone, welcome to the channel. I hope you all are doing great. So we were discussing about our previous year questions of the UPSC Geoscientist exam, and in that we have started with the physical chemistry portion. Now the next chapter that we are gonna discuss is the solutions and the colligative properties. Okay, for this all the questions that have been asked from your year, that is your 2020 to the year 2025, each and every single question of this particular chapter we will be discussing in this video. Okay, so let us begin this. So before starting the video, if you are coming to the channel for the first time, make sure you subscribe to the channel, do hit the like button also for the video if you are understanding the concepts, and do share it with your friends as well. So let us begin now. So firstly, this is me, your Sejal Setia, your chemical sciences mentor, and these are some of the exams that I have qualified. Okay, so the first question of this chapter is there on your screens. So if I talk about the solution and colligative properties chapter, generally in your net or the GATE syllabus, this chapter is not there. No question has been asked in these exams. But if you look upon to your IIT exam syllabus or your that 11th or 12th JEE NEET syllabus, if you look upon that, these chapter is generally being asked. And also you are seeing in the GSI also this chapter is being asked. So generally a gap is there between the JAM exams and the GSI exams because the students generally face the NET and GATE exams in between. So in that this chapter generally we forget. But if you do the previous year questions, you can easily analyze the questions are not much difficult from this one. Okay, so let us begin the first question. It says what one of the following colligative properties it can provide the most precise molar mass of the peptides. So peptides, we know that these are your polymers of the amino acids. To find their molar mass, firstly, what is this colligative properties? Colligative properties means the one which is dependent only on the amount of the substance. They are not dependent on the nature of the substance that you are having. Okay, so this is your colligative properties. Four to five of the colligative properties are there that we generally study in this chapter. That is your relative lowering and vapor pressure. You study about the depression and freezing point, elevation and boiling point, and the osmotic pressure. These four are only there that we study in this chapter. Now, to the most accurate one that we study is the osmotic pressure. This osmotic pressure, it has the relationship that pi, that is the osmotic pressure, it is equal to CRT, where C is the concentration and this is taken in the molarity. This is taken in the molarity. Rest all of the properties that I have told, be it your relative lowering and vapor pressure or depression and freezing point or the elevation and the boiling point that you are having. In all of them, either the mole fraction or the molality will be used. But this is the only one in which the molarity term is present. That is why this is considered as the most accurate, I guess, the colligative property that is used for the determination of your molar masses. So the most accurate is the option B in this case. Okay. Next one we have is this question. It says at 298 Kelvin, the total vapor pressure in the torr for a mixture of a volatile components A and B is given by this much. So you are having, suppose this is a beaker, it is saying it is there, and two of the components we are having A and B. These both are in the gaseous phase you are having. So this A gaseous moles will be exerting some of the pressure and some of the pressure will be exerted by this B molecules. The sum total of their pressure, that is your P total, will be the partial pressure of the A plus the partial pressure of the B you will be having, right? And we know that partial pressure we can write it as it is P naught of the A into the XA. Now what is this P naught of A and the XA? Suppose in the same beaker, now here both of the components were present. Suppose in that same beaker, if only the component A is present and all this vapors of this particular component, how much pressure they are exerting, that is known as the P naught of the A. Similarly, if the same in the same beaker only the B components are present, the pressure that is exerted by these molecules, it is called as the P naught of the B. Okay. Now, since you are taking the mixture of these, some amount of the A you are having and some amount of the B you are having, and you take this in the another beaker, both of them these you have added. So their pressure will be dependent on the mole fraction of the particular component. That is what is written as XA. That is representing the mole fraction of the component A that you are having. And the partial pressure of the B, it will be P naught of the B. That is the pressure the B component would have exerted if only the B component is present in the beaker into the XB, that is its mole fraction. The sum you can present it. Now the sum total of these two components in the beaker, that is the mole fraction sum, that is your XA plus the XB. This sum it will be equal to the unity. Now we can write this XA as 1 minus of the XB, because mole fraction sum is always gonna be equal to the unity. These two components are only present. Had it been the scenario that more than the two components, then that would have also been added over here. Alright. Now this substitution for the mole fraction of A, we can make it into our expression, that we can write it as P naught of the A into the 1 minus of the XB plus of the P naught of the B into the XB. Why in this term we have written? Because you see the total AP expression that is given to us, it is in the mole fraction of the B component it is given. That is why we are bringing it into that form. Okay. So it will become now P naught of the A minus of the P naught of the A into the XB plus of the P naught of the B into the XB. So these two you can collect it from here, that minus of the P naught of the A plus of the P naught of the B into the XB. This will be there, and here the plus sign I am writing, and this is equated to the total pressure that is given to us as 120 minus of 75 into the XB. Just equate these now. You can see that P naught of the A, it is equal to the 120. So P naught of the A you are having it as 120, and this difference, that is PB naught minus of the P naught of the A, this difference you are getting it as minus of the 75 you are having. From here P naught of the B, it will be P naught of the A minus of the 75, it will be 120 minus of 75, that is 45. So this will be the pressure that the P naught of the B it will be there. Right? So P naught of the B value we have calculated, and P naught of the A value also. This is what we wanted to find it out, that what is the vapor pressure of the pure components A and B. Pure means the P naught of the A and the P naught of the B. That means what pressure these individual components are gonna exert when no other component is present in it. So 120 and 45, the correct matches in the option C it is given to us. Okay. Next so one, next question we have is this one. It says which one of the following equations it presents the correct relationship between the relative lowering of vapor pressure and the osmotic pressure for a dilute aqueous solution. So we know that PV is equal to the nRT, where N is the number of moles, R is the gas constant, T is your temperature, P and V are your pressure and the volumes. Right? Now we know that number of moles we can write it as given weight upon the molar mass into the RT. This will be equal to the PV. Now P will be, we can write it as given weight upon the volume into the RT by the M. Like this we can write it. So mass upon the volume, it is my density. So it will be written as rho RT by the M. This is equal to the pressure. So this is one of the relationship. Now we also know this thing, that my lowering of the vapor pressure, lowering of the vapor pressure, vapor pressure. So now what is this lowering of the vapor pressure basically term means? Suppose you are having a beaker, and in this you are having the liquid molecules you are having, and they are exerting some amount of the pressure. So this is the liquid you are having. Now this liquid, this is in a closed beaker, suppose you are having some amount of the pressure, it will be exerted. Now if from the outside medium you are adding a non-volatile solute to it, non-volatile solute it has been volatile. Non-volatile means the one that cannot form the vapor. And here the liquid that you were having, it was the volatile liquid. That means it can form the vapors. So some amount of the pressure this liquid was exerting. Now after the addition of the non-volatile solutes, what is gonna happen? These non-volatile solutes, they will occupy some of the space in the liquid. Like in the upper face of it, some non-volatile liquid will be present. Now that pressure which is being exerted will be different. So initially the pressure they were exerting, it was pure P naught. That means when the individual liquid we were having, when the non-volatile solute we have added, it is the pressure of the solution it will be there. Why it is less? Because non-volatile solutes that we have added, they are occupying some of the space above the liquid. So lesser amount of the pressure it will be generated. So some change in the pressure will be there, that is denoted as delta P, which is equal to the P naught minus of the pressure that is of the solution that we have. Okay. So this change in the pressure that you are having, it is proportional to the osmotic pressure, which is your pi that we have. Okay. So we can write this thing that my delta P, it is equal to K into the pi, we can say, for removing the proportionality constant. So this relative lowering in vapor pressure you are, it is not the relative, it is lowering in the vapor pressure. So if you divide this first equation and the second equation that we have obtained, we will be reaching to our final expression. So delta P is equal to the k pi. In the denominator, it will be the p, and here it is rho rt upon the m. So m we will be bringing it into the numerator now. If you take k equal to the 1, so this can be eliminated from here. So let me just add the slides. Just a second. So here we were having that this relationship we have got it, k value equal to the 1, so it will become my delta p by the p, it is equal to the pi m upon the rho rt. This relationship we have got so far. Now next is, we can write this, that delta p by the p, it was rho, sorry, it was pi m upon the rho rt, right? Pi into the m upon the rho RT. This rho you can write it as mass upon the volume, because this is your density only. So this is by n, where the mass upon the volume into the RT. This mass and this mass will get cancelled out. So this V, it is going to go in the numerator. So pi V upon the RT. So this is the relationship that you are having. Delta P by the P, it is equal to my pi into the V upon the RT. So this is relationship between the lowering of the vapor pressure and the osmotic pressure, right? So delta P by the P, that is equal to the pi V by the RT, that is given to us in the option A over here. Okay. Next is, we have this question. It says a 1% aqueous solution of a certain mass, it is isotonic. Word iso means the same, and here the tonic means the same osmotic pressure. It means the same osmotic pressure. I'm explaining each term because I know students generally have forgotten this chapter, so as much as possible through the previous years, we will be clearing the concepts. Okay. A 1% aqueous solution which is given to us mass by the volume. So this is also your concentration term. A 1% mass by the volume term, it means 1 gram of this particular solute, 1 gram of the solute is is present in the 100 ml of the solution, because here the volume it is given, so ml will be used. 100 ml of the solution. Had it been like 1% mass by mass, at that point it means 1 gram of the solute is present in 100 grams of the solution. Okay, so this is how the various concentration terms we use to present it. So this is one of the solution of a certain substance. It is that it is isotonic, means it is gonna have the same osmotic pressure with a 3% solution of the glucose. So 3%, it again, it is your mass by volume only because one time they have presented it. So the other solution we are having is 3% solution of the glucose, which means 3 gram of the glucose is taken in the 100 ml of the solution. Okay, and its molar mass is given at a given temperature. What is the molar mass of the substance? That is the this one, that solution, that is of the 1% we are having. So here we know the osmotic pressure, that is of the 1%, it is equal to the osmotic pressure that is of the 3% glucose solution that we are having, right? So this is, we have derived it, the term that is the, it was isotonic in the nature. They are having the same osmotic pressure. So osmotic pressure, we know it is, can be written as CRT. So this is for your 1% solution. And for the 3% solution, it is CRT. This is 3%, that is of the glucose. Here the details you have to add it. Now the concentration, as I told, here the concentration, it is in the terms of molarity. And we know this molarity, it is defined as number of the moles of solute, number of the moles of the solute upon the volume of the solution in the liters. This is the definition of my molarity. So concentration, here we can write it as, now here you are having 1% solution, which means the given weight of solute we are having is 1 gram. Its molar mass, we need to find it out. These are the number of moles of it. Now the volume of the solution, already it is given that this is my 100 ml solution, right? So ml you can convert it or you can keep it as it is, because on the other side also the same volume is given. So this is my concentration into the RT. This is equal to, now 3% of the glucose solution. That means 3 gram of the 3 gram of the glucose is there. So given weight of the glucose is 3 gram. Its molar weight we have is 180 grams upon the volume of the solution, which is my 100 ml into the RT of it. Okay, so this RT and this RT will get cancelled out. This volume terms, they will get also cancelled out. So 1 by m we will be having. So from here you get the relation 1 by m, it is equal to 3 upon the 180. So this is in the grams you are having, and this is also in the gram per mole we will be having, right? And here the mass, it is your 1 gram we are having it, right? So with this gram will get cancelled out. So mass we can find it out. This is equal to the 60, right? It is in the 60 grams per mole. But we need to find the weight. It is in the kilogram per mole. So just do the conversion over here, divided by a factor of 1000. So we will be getting it as 0.60 in the kilojoules per mole of it, right? So, sorry, not the 0.6, you will be getting 0.06. So 60 divided by the 1000, you will be getting it as 0.06 kg per mole of it. So this is gonna be the weight of the substance. So answer would be the option D in this case. Okay. Moving upon to the next one we have is this. It says, which of the following is the correct order for the osmotic pressure, which is equimolar solutions you are having of the glucose, sodium chloride and the barium chloride. So we are having this glucose and we have sodium chloride and the barium chloride. So here a Van Hoff factor, it comes into the role, because if you see osmotic pressure, we write it as CRT. This is used, this equation we generally use for the solutions in which there is no association or the dissociation it is taking place. But here these molecules, which is your sodium chloride and the barium chloride, being electrolytes, they dissociate into the solution. So there are different ions which are being produced. They also are being counted in calculation of the colligative properties. Okay, so a factor of I is denoted over here. This I is called as the Van Hoff factor. This is called as Van Hoff factor, right? So what is this Van Hoff factor? Basically, it is defined as the ratio of the total number of the moles which are formed after the dissociation or the association upon the original number of the moles of that particular electrolyte that you are having it, In the case of the glucose, here no dissociation would be occurring, so it is your the I value will be equal to the 1 only. For the sodium chloride we know it is gonna dissociate to give the sodium positive and the Cl negative. So two of the ions are getting being produced. So after the dissociation, two ions, initially only the one it was present. So I factor it will be 2 over here, right? Next is for the barium chloride. So barium chloride, it's gonna dissociate to give us barium 2 positive plus 2 Cl negative. So overall 3 ions are getting being produced. So I value in this case it is equal to the 3 over here. Now you can see that pi is equal to the ICRT. So osmotic pressure is proportional to this I factor we are having. Now equimolar it is written. So the concentration terms they are saying it is the equal only. RT being the constant. So pi value it is dependent upon this Van Hoff factor only. More is this I value, higher will be this osmotic pressure. So maximum we are seeing it is in the case of barium chloride where the 3 I value it is there. So maximum it will be for the barium chloride followed by your sodium chloride and the least one we will be having it for the glucose. Okay, so this is gonna be the order. So we are having barium chloride, sodium chloride and the glucose in the option C we are given. Okay, moving upon to the next one, we have is this question. It says a 0.05 molar aqueous solution of potassium ferrocyanide you are having. It freezes at this much temperature. Its degree of dissociation will be. So we need to find its degree of dissociation, which means the alpha value we have to find this out. So we are having this K4 FeCN6, right? If I see its dissociation, it is gonna give me 4K positive plus FeCN6 4 negative. This is the molecule, this is the ions that we will be getting. So if initially you are having suppose 1 mole of the potassium ferrocyanide, in the starting nothing of it will be formed, right? After that dissociation it will be taking place. Suppose up to the alpha extent this molecule it has ionized. Now here the 4 moles 4 alpha it will be the ions of the potassium ion that will be formed, and alpha because no coefficient is there, so alpha will be the ions which is of the FeCN6 4 negative it will be formed. Now if I see upon this I value that we have said that it is the final number of the moles which are getting being formed, that is 1 minus alpha plus the 4 alpha plus the alpha, because these are the total number of the ions which are formed afterwards, right? And initially how many moles we were having, that is your 1 mole we were having it, right? So this and this will get cancelled out. So I value is equal to the 1 plus of the 4 alpha. So this is the relationship. I is equal to the 1 plus of 4 alpha. Now you see that to calculate this alpha value, you need is this Van Hoff factor value. That is this I value we wanted. So here you see, here the freezing, about the freezing they are talking about. That means the colligative property, which is your depression in the freezing point, it will be used. That means again just like the lowering and vapor pressure I have told, that initially suppose some liquid you are having which is volatile, it is generating some pressure, and then you add the non-volatile solute, some pressure is decreasing over here. In the case of freezing points also, this thing happens. Initially, you are having some solvent and you measure its freezing point. Then you add the non-volatile solute to it and measure the freezing point. So a depression in the freezing point you are observing it. That is denoted as delta TF. It is equal to the TF naught minus the TF. So TF naught is the pressure, is the freezing point that you are having for the original solvent, and TF when the non-volatile solute you have added it. It has been found that this depression in the freezing point, depression means a decrease is there. It is proportional to the molality of the solution. Okay, this here is the term, or concentration term here is molality. Okay, so we know that removing this proportionality constant, the constants that is added, it is the Kf into the molality. It is called as the depression in the freezing point constant you are having. Okay. Now, some of the molecules, as I said, the solvent molecules that we will be having, they can show the association or the dissociation. So, I factor, that is the Van 't Hoff factor, is included in front of it. So, this is the depression in the freezing point, and this expression it will be used to find the value of this I over here. Okay. So, delta TF, it will be, they are saying that it is freezing at this much temperature. So initially you can take it as 0, and the final temperature it is your minus of the 2.6 minus of the 0.26 degree centigrade, 0.26 degrees centigrade. You can keep it in the Kelvins or the degree centigrade, because here water it is also freezing at 0 degree centigrade, and when the solute you have added this to it, then at this much temperature the freezing is taking place. So you can present it in the degree centigrade because that's the change we wanted over here, right? So here it will be the 0.26 degrees centigrade. This is equal to the I into the Kf value that is given to us as 1.86, I guess, 1.86 grams per mole, and the molality of the solution, that is 0.05 molar it is given, 0.05 it is given. So you can find the value of the I from here. I you will be getting it as this, you will be solving and getting 2.79. Right, this is gonna be your I value. Now we have got that my I value, it is equal to the 1 plus of the 4 alpha from the previous, after the dissociation we have considered this expression, we have got it. Just substitute the values, we will be getting 2.79, that is equal to the 1 plus of the 4 alpha. So 1.79 upon the 4, it will be your alpha. This is gonna be, if you wanted percentage, so alpha percentage if you wanted, so multiply it with the 100. So solving this, we are gonna get the value as 45%. So degree of dissociation, it will be my 45%. Okay. So answer would be the option C in this case. Okay. Next one we have is this question. It says, what will be the value of the freezing point depression constant? That means Kf value, this time they are asking, of the cyclobutane, which is having a freezing point of 280 kelvins, and the molar enthalpy of the fusion is given as this one. So this is a direct formula you just have to remember for this one. That is your Kf value, it is equal to the R, which is your gas constant, into the TF square, which is the freezing point temperature, its square you needed, upon the LF, which is your vaporization enthalpy of fusion that you have, into the 1000. And here in the numerator you just have to multiply it with the molar mass. So Kf is RTF square into the M upon the LF into the thousands of it. So R is my gas constant, TF is the freezing point, freezing point, and next is LF, that is your enthalpy of the fusion, enthalpy of the fusion, and M is the molar molecular mass over here, molecular mass. So here it is talking in to find the freezing point depression constant. Had it been the boiling point constant if it is being asked. So there also the same formula will be there. Just instead of the freezing point, at the boiling point it will be there, and enthalpy of fusion, there the enthalpy of vaporization it will be given over there. Okay. So Kb value you can find it from there. Now for the y, just substitute the values over here. So Kf, it will be equal to your 8.314 in the joule per mole per Kelvin into the 280 Kelvin square we wanted, RTF square, into the molar mass of it, that you will be given as 56 grams per mole, right? And in the denominator we have the values, that is your 2.68 into the kilojoules per mole. So 1000 joule per mole into a factor of the 1000 we have to take it over here. So units if you see, so joule per mole and this joule per mole will get cancelled with the per Kelvin one of this Kelvin, it will get cancelled out. So the value of the Kf we will be having it as 13.64 into the Kelvin gram per mole. Okay, so unit conversion also from this you can see that which of the units are getting being answered. From that also you have to pay attention and which of the units the answers are being asked. So in this case the answer is the option C over here. Okay, now moving upon to the next one, you have this. It says a cell is bathed in a solution that has a greater osmolarity than the cystole. The solution is described as. So we have different types of the solutions. I told we have seen the isotonic one, where isotonic it means the same osmotic pressure you are having. The same osmotic pressure it is there. Other terms we use is that is the hypertonic solution, where we have a greater amount of the osmotic pressure. So here it means the more osmotic pressure it is there. More osmotic pressure. And the hypotonic hypotonic solutions where the less osmotic pressure it is there, less osmotic pressure. So here the term is used as a greater osmolarity it is there, which refers to the fact more osmotic pressure. So solution it will be called as my hypertonic solution. Okay, now next is we have this question. It says which one of the following aqueous solution it has the lowest vapor pressure at the room temperature. So we know this thing that the depression in the freezing point, or the depression that is lowering in the vapor pressure delta P, it is equal to the generally the expression that you observe that is of the relative lowering in vapor pressure. A relative lowering in the vapor pressure. So relative term is used when with respect to something we are talking about. So we have seen that for a pure solution you will be having P naught pressure and some amount of the decrease is there in the pressure, and relative it means with respect to something. So with respect to the original pressure if you take it, that is no non-volatile solute you are adding to it, this is equal to the XB, which is the mole fraction of your solute component. This is the mole fraction of the solute. This solute is not showing any association or the dissociation. Okay, so this is the thing. Now you can see here the solutions that is given to us. It is 0.1 molar hexaamine cobalt chloride, barium chloride, glucose, and the tris-ethylene diamine copper to sulfate. So these are the one which are either showing the association or the dissociation. So a I factor that is of the Van Hoff factor it is also included over here. Okay, so we can say that this I factor is playing the role in varying this lowering in the vapor pressure. So we can say that P naught minus of the P it is proportional to this I factor. Other things keeping to be the constant because concentration terms if you see they are all of the 0.1 molar concentration only. So we can say that P naught minus of P it is equal to Ki, right? Removing this proportionality constant. So P naught minus of the Ki, this is gonna be equal to the P. That means this is the vapor pressure of the solution that we will be having. So this P is dependent upon this I value. Now for the given solutions, if you see that is hexaamine cobalt chloride, hexaamine cobalt chloride. That means this one we are having NH36 and cobalt is in the plus 3 oxidation state. So Cl3 it will be there. If it is undergoing the dissociation, this is gonna give us cobalt NH36 3 positive plus 3 Cl negative. That means total of the 4 ions it will be producing. So I value in this case it is gonna be 4. Next molecule is my barium chloride, which is BaCl2. That is gonna dissociate to give barium 2 positive plus the 2Cl negative. So I value in this case it is gonna be equal to the 3. Total 3 ions are being produced. For the glucose, the I value it is gonna be equal to the unity only because it neither shows the association nor the dissociation. Next is tris ethylene diamine copper 2 sulfate. So copper and tris ethylene diamine, which is En, and 3 units of it they have taken it, and this is gonna be SO4. So on dissociation, this is gonna give you cobalt, sorry, copper it is there, no? Yeah, copper, En, 2 positive plus the sulfate, 2 negative it will be there. So that means here the 2 ions are being produced. So I value over here is 2. So here if you see, more is gonna be this I value, lesser will be this pressure, right? So I, it increases, the pressure it is gonna decrease because something is getting being subtracted from here. From this relation you can observe this. So the maximum value of the I we can see it is in the case of the hexamine cobalt chloride, where I value we are having is a 4, right? Whereas for the other one it is the either 3, 1 and the 2 values we are having. The maximum one is 4. So maximum decrease you are gonna observe in this case. So in the case of hexamine cobalt chloride, so lowest vapor pressure it will be for the hexamine cobalt chloride where the maximum I value we were having that. Okay. Next is we have this question compared to the pure water, 1 molar sugar water solution. So pure water, initial solution, initial solvent you are having, and the 1 molar sugar water, it means that the non-volatile solute you are adding it. So what change you are gonna observe? We will be having the lowering of the vapor pressure, lowering of the vapor pressure. We will be having elevation of the boiling point, elevation of the boiling point, and you will be observing the depression in the freezing point. Depression in the freezing point. So these are the things that you will be observing. So first is lowering of the vapor pressure, lower vapor pressure. The next is they are saying lowering of the boiling point. So this one is incorrect. Boiling point is gonna increase over here. In the B option, it is saying lowering of the boiling point. So this is also not the correct. Lowering of the vapor pressure, high boiling point, and lowering of the freezing point. So this is the correct one that is given to us in the option C. Right. Next is we have this station. So the relationship between the osmotic pressure and the lowering of the vapor pressure for an infinitely dilute solution. So this relation you have is pi is equal to the RT by the V naught natural log of P by the P naught of it. So this is the relationship which is given to us in the option B over here. Next is this one. The vapor pressure of the ethyl acetate at 293 Kelvin, it is given as this much. The vapor pressure of the solution that you will be having, which you are obtaining by dissolving zero point 0.4 grams of the non-volatile solute, which is of the molar mass 60 grams per mole in 100 grams of ethyl acetate at the same temperature. So here the concept of the relative lowering in the vapor pressure, it will be used over here. Alright, so we know that the relative lowering in the vapor pressure, it is equal to the P naught minus of the P upon the initial pressure P naught, it is equal to the mole fraction of the solute. Right. So now we want to find this P value that is of the solution, the vapor pressure that you will be having. P naught value we are given that is 72.8 minus of the P upon 72.8. This is equal to mole fraction of the non-volatile solute that we are adding to it. So non-volatile solute given with mole fraction, it will be equal to the number of moles of this upon the total number of the moles that is of the solution, which is of the solute plus the solvent, plus of the solvent. Where this NV it represents the solute number of moles. Okay. So here the solute given weight we are having is zero point 0.4 gram. Its molar mass we are having it as 60 grams per mole. In the denominator also 0.4 upon the 60 plus the mass of the solvent, solvent that you are having, that is given to us as 100 grams. Now the molar mass of ethyl acetate that we calculate, it will be your 88. So just solve this and find the value of the P from here. So we are having this 1 minus of P by 72.8. This is equal to your 0.4 upon the 60 upon this fraction, that is 0.4 upon the 60 plus of 100 upon the 88. So solving all this, the pressure that we will be getting, it will be your 72.37 torr pressure. So this is gonna be your answer, 72.37, that is given to us in the option B over here. Okay. Next one we have is this question. A statement based it is given. It says people with the high blood pressure, they are advised to take lower intake of the salt. This we know that one who is suffering from the high blood pressure, generally the doctors advise them that they should consume the less amount of the salt in their food. Why is it so? Because you are saying that higher intake of the salt, it is gonna cause the higher osmotic pressure. I told this thing, when the higher osmotic pressure, that means hypertonic solution it will be formed at that point. Right? So this statement is the true that if we consume the more amount of the salt, high osmotic pressure it will be produced. Next is, it says it results into the greater inflow of the water in the cells and causes the water retention in the tissue cells and the intracellular spaces. So what basically is happening, if you take more amount, this is the cells that we are having in our body. If you take more amount of the salt, so the outside solution, it is gonna have the more amount of the osmotic pressure. It is gonna have the higher osmotic pressure it will be there. When the hypertonic solution you are having, so here the cells, they are gonna release the water into the this part in the outside world, they will be releasing the water. That means they are gonna shrink in the size. Here they are saying that there will be the inflow of the water in the cells. Water is not going into the cells. This thing is not happening. Reverse of this it is happening. That is when it is placed in the hypertonic solution, it is gonna shrink at that point. Cells will shrink because water content it is higher in the cells, and in the outside solution the water content is the lower one. So the side where there is more amount of the water content, from that side to the other side where the lower amount of the water content is there, the flow of the water it takes place in the osmosis process. So here these molecules, they are gonna shrink in this case. So this statement is the reverse of it. So this one is your incorrect. So only the statement one is only correct over here. Okay. Next one we have is this question. It says the equation pi is equal to C2RT, where C2 is number of the moles upon the volume, that is the molarity. Concentration it is given is the molar concentration of the solute. The others have the, that means they are just asking what is the name of this particular equation. So this is your Van Hoff equation. This is my Van Hoff equation. Okay. The other equations, if you see, that is your Raoult's law. This is related to the total pressure of the solution. The total that we have used is, it is the P naught of the A into the XA that was given to us this Raoult's law. That is partial pressure, this mole fraction of the particular solvent into the initial, that is P naught of the solvent plus the P naught of the solute that you will be having into the mole fraction of the solute. So this is your Raoult's law. Next is Henry's law. This is for the gas dissolved in the liquid, that is the pressure, it is equal to the Henry's constant into the mole fraction of it. Okay. Next is the Walden's rule. So this is for the, this is written like lambda of the equivalent, it is equal to the this eta value, it is equal to the constant, which is equal to your z into the f e naught upon the 6 pi into the R. So these are the equations. So the first one, that is of the pi is equal to the C2 into the RT. This is your one thought equation. Okay. Next one we have is this question. The boiling point of the chloroform, it was raised by this much value. That means the change in the boiling point it is given to us. Then this much amount of the non-volatile solute, it was dissolved in this much amount of the chloroform. What is the molar mass of the solute? So we have delta TB, that is elevation in the boiling point. This is TB minus of the TB not of it. That means after adding the non-volatile solute of the solution, this TB value it is higher. So from the higher value, this of the pure solvent it has been abstracted because we want that delta TB it should come out to be the positive. In case of the delta TF, it was TF not minus of the TF, that was depression in the freezing point we were having, and here is elevation in the boiling point. So here it is given that this value, that is of the delta TB, it is equal to your 0.325 kelvins of it. Okay. Just like for the depression in the freezing point, we have seen it. The elevation in boiling point is also proportional to the molality of the solution, and delta TB, removing this proportionality, you get the ablioscopic constant, and Kf was called as the either the depression in the freezing point constant, that is called, or it is also called as the cryoscopic constant. This is called as the ablioscopic constant or the elevation constant of the boiling point into the molality. Here, if the molecule is showing the association or the dissociation, so there also this I factor it will be included. Okay. So these are the expressions for your elevation in the boiling point. Now, chloroform is there. It does not show any association or the dissociation. So this expression we are gonna make use. So delta TB, that will be equal to the Kb into the molality. Now, what is this molality term over here? Molality, it means the number of moles of solute, number of moles of the solute upon the weight of the solvent in the kgs. Solvent in the kgs. In case of molarity or the normality, volume is used of the solvent. For the molality, it is weight of the solvent in the kgs. So just this thing we have to use. Delta TB value it is given to us, which is 0.325. KB value it is given to us as 3.9. 3.9. Now the molality is number of the moles. So the given weight of the non-volatile solute you are having is 5.141 into 10 raised to the power of minus of 4. It is given to us in the kgs. Its molar mass we have to find it out. So this is the molar mass of the non-volatile solute. We have to find it upon, in the denominator now it is weight of the solvent in the kgs. So that is the chloroform. Its mass is given 35 into the 10 raised to the power of minus of 3 in the kgs you will be having it. So just we need to solve this and find the molar mass. Okay. So this value we have got it as, just take it on this particular side, 0.325 into the 35 into 10 raised to the power of minus of 3. This will be equal to your Kb value, that is 3.9 into the 5.141 into 10 raised to the power of minus of the 4. So just here the m value it will be there. So just m value when we will be calculating, it will be your 0.176 kgs per mole of it. This is gonna be the molar mass of the non-volatile solute that is added to it. So 0.176 kgs per mole, that is given to us in the option B. We will be having it. Next is we have this question. It says P is the total pressure of an ideal binary liquid solution if Ya and Yb are the amount fractions of the constituents in the vapor phase, then which of the following statements is the correct? So we know this, the partial pressure, it is equal to the mole fraction into the P total of it, right? This relationship we know. So P total in this case, it will be Pi upon the mole fraction, that is your Yi of it, or we can say 1 by P total, it is equal to the Yi upon the Pi of it, right? So instead of the 1 by P total, here P is used for the total pressure term, right? So this will be written as 1 by P is equal to your mole fraction, that is of the ith component, upon the Pi of it, that is of the partial pressure. So it is gonna be relationship is 1 by P. So compare it with your y is equal to mx equation, mx. So this slope value is 1 by Pi and the x value is this mole fraction term. So the plot we are having is for the 1 by P versus the YA or the YB, that is of the YI, it varies linearly. Linearly it is varying because of the straight line equation is being used. Y is equal to the mx. So 1 by P varies linearly with the mole fractions. So this is given to us in the option. About the origin, we are not getting anything from here. So 1 by P versus YA and the YB, it will be used over here. Okay. Moving upon to the next one, we have is this question. It says which of the following solution in the water was of the lowest vapor pressure? So again, similar type of equation already we have discussed, that P naught minus of the P, that is lowering in the vapor pressure, it is equal to the I and to the where the in the denominator this relative lowering in vapor pressure, it is proportional to their mole fraction of the solute basically. So we can see that P naught minus of P, it is proportional to the I value, right? So P naught minus of the P, it is equal to the Ki over here. K is proportionality constant we are using. So the pressure of the solution that you are getting after the addition of the non-volatile solute, it will be equal to P naught minus of the K into the I of it. That means my pressure, it is inversely proportional to this I value. When this I value it is increasing, the pressure value it is gonna decrease over here. Right? This is what we are getting from this expression. So now we will be calculating the I value for the different solutes that have been given to us. So it is barium chloride. It's gonna dissociate to give you the barium 2 positive plus 2Cl negative. Right? So in this case, the I value will be 3. Okay. Next is for the sodium chloride. We are having it will gonna give us sodium positive plus the Cl negative. So 2 will be there, the I value. For the KCl, again K positive plus the Cl negative. 2 ions will be formed. For the urea, it's gonna undergo no dissociation, so I value will be 1 over here. So maximum I value you are having it in the case of the barium chloride. That means the lowest vapor pressure it will be in the barium chloride only. So the correct answer will be the option A in this case. Okay. Next one we have is this question. It says what is the mass of the mass of solute which is having the molar mass this much that should be dissolved in 180 grams of the water to reduce its vapor pressure to 23 torr at 25 degrees centigrade. Approximately we have to find it. The vapor pressure of the water at 25 degrees centigrade it was 24 torr. So they are saying for the pure water the vapor pressure is this much. After the addition of some solute it has reduced to 23 torr. What is this amount of the solute that we have added to have this much amount of the lowering in the vapor pressure? Okay, so P naught minus of the P upon the P naught, this is equal to the mole fraction of the solute. So the initial pressure we were having is 24. After that solution we have obtained, it will be 23 upon the 24. This is gonna be equal to the mole fraction of the solute. Given weight of the solute, we have to find it out. Molar mass of the solute it is 360. In the denominator, the mole fraction sums it will be there. So x upon the 360 again. For the water it is 180 grams. Molar mass of water is 18 grams per mole. So this is gonna be 10 over 5. So just solve this. It will be 1 by 24, which is equal to your x upon the 360 upon the 10 plus of the x upon the 360. This 360. Just solve this and find the value of your x here. So x we will be getting it as 150 grams from here. So the molar mass, that is of this much amount of the solute when we are adding it to the water, this much amount of the fluorine in the vapor pressure we will be having. Okay, now the next question we have is this one. It says for a binary A plus B ideal solution, the total vapor pressure of the solution is given as. So we know this thing that P total is partial pressure of A plus the partial pressure of B, which we can write it as P naught of A into the XA plus the P naught of the B into the XB of it. Right? So now XA plus the XB, that is the mole fraction sum, it will be equal to the unity. We can either write in terms of the XA or in terms of the XB. So if XA we find it out, it is gonna be 1 minus of the XB of it, or we can write it as XB is equal to the 1 minus of the XA. Either of the terms you can use it. Just we make sure that in the final expression it should be either XB or the XA. So I can see more of the options XA in terms of XA it is there. So let us take it in terms of the XA only. So XB substitution we are making it. So P total it will be equal to the P naught of the A into the XA plus the P naught of the B into the 1 minus of the XA of it. So we can say P naught of the A into the XA plus of the P naught of the B minus of the P naught of the B into the XA it will be there. So we can write it as P naught of the B plus of P naught of the A minus of the P naught of the B into the XA. This is the expression that is for the P total you will be having it. So we can see it is given to us in the option B over here. P total is P naught of the B plus of the P naught of A minus of P naught of the B into the XA. So the correct answer is the option B over here. Okay. Moving upon to the next question we have is this one. It says a 0.002 molar sugar solution in the water. It is separated from a pure water by an osmotic membrane. The osmotic pressure which is developed at 27 degrees centigrade is. So osmotic pressure, very simple. We just have to find this out. It is equal to the ICRT CRT or the ICRT. For the sugar solution, I value it will be equal to the 1 only. So pi is equal to the CRT only. So osmotic pressure, it is now here the molarity it is there. Given number of the moles or the concentration directly it is given to us as 0.002 molar, 0.002 molar into the R value which is 0.083 decimeter cube bar per Kelvin per mole per Kelvin per mole into the temperature which is will be of the 300 Kelvin. So with this Kelvin, this per Kelvin term will get cancelled out and this is molar, that means mole per decimeter cube. So this mole and this per mole term it will get cancelled out. And this per decimeter cube and per decimeter cube it will be cancelling out. So pi we are getting it as in terms of the bar pressure you will be obtaining it. So that you are getting it as 0.0498 bar pressure of it. But you are seeing the final answer, it is in the kilopascal that is given to us. So in that we have to make the conversions. We know that 1 bar is 101325 pascals of it. Right, so just substitute this 0.0498 into the 101325 upon the thousands because kilopascal you wanted. Solving this, you are gonna get your answer as 5.045 kilopascals of it. So this is gonna be the answer 5.0. So approximately this the answer it is matching over here. Okay. Moving upon to the next one we have is this question. It says a 0.1 molar solution of a monobasic acid is 10% ionized in the water, the freezing point of the resultant solution, we have to find that. So we need to find the value of the TF over here. So delta TF we know that is equal to the TF naught minus the TF. So this TF value you need to find this out. Okay. So the solution we are having is of this acid which is gonna dissociate as H positive plus the X negative of it. Right? It is showing this 10% ionization, that means alpha value it is 10 over here. Initially suppose 1 mole of it you are having. So this is in the start it is 0. So some alpha amount of it has dissociated. Here the alpha of it has been formed. Here also this alpha of it has been formed over here. So if I calculate the I value from here, I'll be getting 1 minus alpha total final number of the moles which are getting being formed, which is the sum of all of this plus alpha upon the initial one, that is 1. So this will be getting cancelled out. So it is gonna come out to be as 1 plus of the alpha over here. Now alpha value we already know it is 10%. So this is 1 plus 10 by the 100 of it. So this will come out to be as 1.1. So this is the I value we have calculated it. Right? Now we know this that delta TF it is equal to the I into the KF into the molality. Right? So delta TF value we will be calculating. I value we have calculated as 1.1. KF value it is given to us, that is 1.86 Kelvin per molar. 1.86 Kelvin per molar, and the molality concentration, that is of the 0.1 molar solution it is given into the zero point 0.1. So delta TF we can find it out from there, that we will be getting it as 0.2046. This is gonna be the value that is of the delta T we will be having it. Okay. Now the delta TF value we know it is equal to the delta TF, it is my TF naught minus of the TF which is equal to the 0.2046. Now the TF value it will be TF naught minus of the 0.2046. So for the water it is given. So for the water freezing point is my 0 degree centigrade and here it is 0.2046 degree centigrade only. So the answer we are getting it as minus of the 0.2046 degree centigrade. So this is gonna be the freezing point over here. Okay. So the correct answer is minus of this one B option it is matching it. Right. So moving upon to the next one now. We have is this question. Match the list 1 with the list 2 and select the correct answer using the code which is given below. So this is the various substances and their Van Hoff factors. We just have to fill that. So for the sodium chloride, it's gonna dissociate to give the sodium positive and the Cl negative. So in this case, I value we will be having it as 2. Right? So NaCl, A matches with the option 3 over here. So with the A we have is 3. Next is for the glucose, I value it is gonna be equal to the 1 only. So with the A, B, C and the D, under the A the code was 3, with the B it is 1. Now with the K3PO4, so K3PO4 it is gonna give us 3K positive plus the PO4 3 negative. So total 4 ions are being produced. So with the C the code will be the 4 over here. So under the D obviously 2 it will be coming. Right. So 3142, 3142 that is given to us in the option B over here. Okay. So very simple question. Next one we have is this question. Two components A and B have their pure vapor pressures in the ratio 1 is to 6. That means P naught of the A to the P naught of the B. It is given to us as 1 by 6. And the respective mole fractions in the solution, which is XA and the XP ratio, it is given to us as 1 by 4 of it. We need to find the mole fraction of them in the vapor phase. So mole fraction in the vapor phase, it is given as the ratio we have is that is YA to the YB. This is the mole fraction ratios you will be having in the vapor phase, or you can say YA and YB are the mole fractions of the components A and B. We need to find out the component B, the mole fraction that is present in the vapor phase. So now we know this thing that part P total into the mole fraction of the component A in the vapor phase. This is equal to their partial pressures. Partial pressures. This will be of the component A. Now for the P total into the YB, it will be equal to the partial pressure of the component B. Partial pressure of the B component. So this ratio you can take it. This is equal to the P naught of the A into the XA, because in this way also we can write the mole fractions upon the P of this partial pressure, we can write it as P naught of A into the XA upon the P naught of the B into the XB. So this relationships you can use it. P total will get cancelled out. So we are having it as YA upon the YB. This is equal to the P naught of A into the XA upon the P naught of B into the XB. And this ratio is already it is given. P naught of A upon the P naught of B was 1 by 6, and the XA upon XB it was 1 by 4. So it is 1 by 24. So the ratios of YA to the YB, we have got it as 1 by 24. Now we know this thing that the mole fraction sum, that is of the YA plus the YB, it will be equal to the unity. You can find this in YA in terms of the YB or YB in terms of the YA. So we will be using that. So it will be 1 by 24 of the YB plus of the YB, that is equal to the unity. So solving this, 1 by 24 plus of the 1 YB will be equal to the unity. It will be 25 upon 24 of the YB, unity is equal to the unity. So we will be getting that my YB it is 24 upon the 25, which on solving we get value as 0.96. So this is gonna be the mole fraction of it in the vapor phase for the component B, that is in the option B we are having. Okay, so just this relationship it was important that the partial pressure in terms of this component that is in the vapor phase we can write it like this, and for the solution phase we can write it like this. Okay. Next is we have this question. It says when 2 grams of the solute it is added in 1000 ml of the pure water, the vapor pressure is decreased by. So how much decrease in the vapor pressure we are obtaining? Where the original vapor pressure of the pure water it is given to us, and the molar mass of the X also is given to us. We know that the relative lowering in the vapor pressure, which is P naught minus of P upon the P naught, it is equal to the mole fraction of the component, that is the solute that we are adding to it. Okay. So this P naught minus of the P only we have to find it out, that we can write it as delta P. Initial pressure it is 2.34 kilopascals, right? This is equal to the mole fraction of the component solute that we have added. So the given weight of it is 2 grams and its molar weight it is 200 grams. In the denominator also the moles of the solute plus of the solvent, that is 1000 ml of the pure water. Density of water is also your 1 gram. So 1000 grams of water it is given. The molar mass of water we have it is 18 grams per mole of it. So just solve this and get your answer. So it is 1 by 100 upon the 1 by 100 plus of 55.5 plus of 55.56 we will be getting. So delta P value on solving all of this you will be getting it as 0.0030 that will be there into the 42 kilopascals of it. So that is given to us in the option B over here. So B is the correct answer in this case. Okay, I hope this is clear. Moving upon to the next one, we have is this question. It says the aqueous solution of K2SO4, which is of this much concentration, it is isotonic with this much amount of the aqueous solution of the glucose. So again, isotonic means same osmotic pressure, same concepts are being used over here also. So osmotic pressure of the K2SO4, this is equal to the osmotic pressure of the glucose. So now osmotic pressure we know it is ICRT, right? And here also it's gonna be ICRT. This is for the glucose. This terms it will be used, and this is for the K2SO4. Okay. We need to find is the degree of dissociation of the K2SO4. For that we need is this I value over here. Okay. So that one which we used to write like this for the NaCl we write the I value as 2, for the barium chloride as 3. That is when we are considering 100% dissociation. But at this point, to some extent it is dissociating. That is why this I value is needed to be calculated. From that we will be finding to what extent the degree of dissociation it is taking place. Okay. So this RT and RT on both sides will get cancelled out. So I into C for this K2SO4, this is equal to I into the C for the glucose. This is for the glucose and this is for the K2SO4. This I value for it we have to find it out. That is gonna be for the glucose I value is 1. Concentration of glucose it is given to us as 0.01 molar and the concentration of K2SO4 it is 0.004 molar. So from here the I value we are getting it as 10/4 we will be getting it. Okay. Next is to find this degree of dissociation. You can see K2SO4, it's gonna dissociate to give 2K positive plus the SO4 2 negative. Initially 1 mole, nothing is being formed. Here the alpha is the degree of dissociation, here the coefficient is 1. So alpha will be there. Here 2 of this 2K positive, that means 2 alpha will be formed. Here this alpha will be formed. If I calculate this I value, finally how many number of moles are being formed? 1 minus alpha plus of 2 alpha plus of the alpha upon the initial one that was equal to the 1 only. So this alpha and this alpha will get cancelled out. That is equal to 1 plus of the 2 alpha. So I value it was 10/4. This is equal to the 1 plus of the 2 alpha. So 2 alpha it will be equal to the 6/4, right? So just solve this. Alpha value you will be getting it as 3/4 into the 100 we will be taking to calculate the percentage. So 25 3 it is your 75%. So 75% is gonna be the degree of dissociation of the K2SO4. Okay. So C is gonna be the correct answer in this. Next is we have this question. It says which one of the following compounds will show the largest increase in the boiling point when it is added to the aqueous solution. So we know this thing that delta TB it is equal to the I KB into the molality of it. So delta TB value it is directly proportional to this I value over here. Considering the 100% dissociation of this solutions, here we have MgSO4, it's gonna give us Mg2 positive plus the SO4 2 negative. So I value it will be 2. Next is for the calcium hydroxide, it's gonna give calcium 2 positive plus 2 OH negative. So I value it will be 3 in this case. Next is for the sodium chloride, it will be sodium positive plus the Cl negative. So I value will be 2. For the calcium chloride, this is gonna be calcium 2 positive plus the 2 Cl negative. So total 3. So one thing is you can see for the calcium hydroxide, also for the calcium chloride, we are getting the I value as the 3 over here, right? But also if you see here the number of moles are also given us to be the different. Here the molality term is also important. So delta TB is directly proportional to the molality also. And molality is nothing but the number of the moles of solute upon the weight of the solvent in the kgs. Weight of solvent in the kgs. So molality delta TB value, it is also proportional to the number of the moles of the solute that you are having. So the one in which the two moles are present, and also this I value is 3. That is in the option B. You can see for the calcium hydroxide here the 2 moles we are having. For the calcium chloride only the 1 mole it is given. So the maximum increase in the boiling point, it will be in the, for the calcium hydroxide we will be having it. Okay. Now the next is, we have this one. This question, it says three particles of the solute A, it associates in the benzene. So here now instead of dissociation you are having this association. So three particles of the A, they are associating to form the one, that is your A3, it will be formed. Okay. What is the degree of the association of the solute A? Is degree of association is given to us to be 0.75. The freezing point of benzene and its freezing point depression constant values are given. The freezing point of this much 0.25 molar solution, how much that is gonna be there. So firstly we need to find is the value of the I over here. Now to find the value of the I, take 1 mole on this side. A is gonna get 1 by 3 moles of this A3. Right? Initially you can say it is 1 mole and nothing is formed. Now here this alpha extent it has dissociated, and here 1 by 3 alpha of it would have been formed. I value, it will be now the sum of the moles which are formed, which is 1 minus alpha plus of 1 by 3 alpha of it upon the initial one, that was equal to the unity, because 1 mole of it we have taken it. So solving this we will be getting it as 1 minus of 2 by 3 alpha of it. This is gonna be the I value. Now the alpha value, it is given to us, that is degree of association, it is your 0.75, right? So the I value, it will be 1 minus of 2 by 3 into the 0.75, that we can write it like this. So 25 3s are and 25 4s are, 3 will get cancelled out, 1 by 2. So I value we will be getting is 1 minus 1 by 2, which is equal to the 0.5 over here. Okay, so this is gonna be the I value. Now we know that delta TF value, it is equal to I into the KF into the molality of it, right? So we need is to find the freezing point of the solution. Its concentration, it is given us as 0.25 molar, and its this freezing point depression constant values is also given, and the freezing point of benzene is also given to us. So we know delta TF is TF naught minus the TF I value we have calculated as half. KF value, it is given to us as 5 Kelvin kg per mole, 5 Kelvin kg per mole, and the molality value we are given it as 0.25 moles. Mole solution it is given. Now delta TF naught, it is also given to us as 5.5 degrees Celsius it is given. It's given to us as 5.5 degrees centigrade minus of the TF. This is gonna be 1 by 2 into the 5 into the 0.25. Okay. So just solve this. You will be getting it as, this is 100, we can write it like this. So 2.5 for the 10 here it will be there. So 625 by the 1000 or the 0.625. Alright. So we can say that TF value, it will be 5.5 minus of the 0.625, which you will be getting it as 4.7, 4.9 approximately the value you will be getting it. So the correct answer will be the option B in this case. So moving upon to the next question we have is this one. It says the experimental results of the colligative properties of the solutions are often found to differ from the calculated values. That is what I was saying with the colligative properties, be it your elevation and boiling point, depression and freezing point, or the osmotic pressure. We include is this I value that is called as the Van Hoff factor. Van Hoff factor. This is being included because the solute particles that we are adding to the solution, it is either showing the association or the dissociation. So either the association or the dissociation is being shown by the concerned solute. It is not that they are behaving like the non-ideal one. This is not the scenario. So one half factor is included. So the correct answer is A in this case. Due to the association or dissociation, the different values you observe. That is why this I factor is included over here. Moving upon to the next, this one, the vapor pressure of the pure water, it decreases from 24 torr to 23 torr on adding x amount of the solute, which is of the molar mass 480 grams per mole in 150 grams of the water. What is this value of the x? We know that the relative lowering in vapor pressure, which is P naught minus of P upon the P naught, this is equal to the mole fraction of this solute particles, which is equal to the number of the moles of the solute upon the number of moles of the solute plus the number of moles of the solvent. Alright, just substitute the values. The initial pressure of the water we are having it as 24 torrs. After adding the non-volatile solute, it has reduced to 23. Upon the 24, this is gonna be equal to number of moles of solute. It is given weight upon the molecular weight. Given weight, we have to find it out. Molecular weight of it is 480 grams per mole in the denominator also x upon the 480 plus for the solvent that is water 150 grams of it we have added, its molar mass is 18 grams per mole of it. Just solve this, you will be getting it as, and taking this on the other side, it will be 1 upon 24. So just find the value of the x from here. So the x value we will be getting it as 167 grams of it. So this is gonna be the answer for this one. Okay. Moving upon to the next one, we have is this question. It says, consider a solution of 50 grams of the enzyme which is dissolved in the water to give 2 decimeter cube of the solution, which means volume of the solution is given at 27 degrees centigrade, temperature is given. The osmotic pressure of the given solution is. That we have to find it out. We know that pi it is equal to the CRT. This is the osmotic pressure relationship we have it. So now here it is given that how much amount of the enzyme was added? 50 grams, because this we have to take it in the molarity, and molarity is number of moles of solute upon the volume of the solution in the liters. So 50 grams of it. The molar mass of it is 9000 grams per mole of it. Okay. And the volume of the solution it is 2 decimeter cube or 2 liters we can say, because 1 decimeter cube is equal to the 1 liter only, into the R, that is 0.083 in the decimeter cube bar per Kelvin per mole of it. Okay, into the temperature which is your 300 Kelvin. So with the Kelvin, this per Kelvin will get cancelled out, and here this gram and gram was getting being cancelled out. This mole it will go in the numerator. So with that, this mole term and this per mole term will get cancelled out. And with this liter, this decimeter cube term, it will be cancelled out. Overall answer, you will be getting it in the bar terms, you will be getting it. So solving this, you will be getting it as 0.069 bar pressure of it. Now we need to convert it into the kilopascals. So again, you can see same concept was there. In the previous case also this osmotic pressure was calculated. The answer you were getting was in the bar and you made the conversion in the kilopascals. So same concepts are being repeated. So we know that 1 bar it is equal to the 101325 pascals of it, or it is equal to 101.325 kilopascals of it. Just substitute this. The pi pressure you will be getting it as 0.069 into the 101.325, which is approximately your 0.69 kilopascals of it, right? Or the how much it will be there? Just this 1000 factor it will be there. So just multiply it with this and you will be getting the pressure as 6.9 kilopascals of it. It's given 0.69, you can just take this, the decimal places. So the correct match will be the option B in this case. Okay, next one we have is this question. It says we consider the following values of the normal boiling points and the molar boiling point elevation constant. So the normal boiling point it is given and the elevation constant, that is Kb value, is given to us for two of the solvents. One is the water and other is this ethanol. Which one of the following solutions it would result into the greatest boiling point elevation? Okay. So we know that delta Tb it is equal to the I into the Kb into the M of it, right? So two factors that are playing the role. One is this Kb value. So more is this Kb value, more will be this delta Tb value. Among these two, if I see, for the water it is 0.52, but for the ethanol it is 1.20, approximately double of it you can say. So for the ethanol, it's obviously gonna be the higher one. So the one in which the water it is taken, that we can eliminate directly. Okay. So on the basis of this Kb value we have eliminated as. Next is we need these vectors. This concentration terms are given as to be the same. So molality you are gonna get the same values only. For the I values also we can take into the consideration, that is for the lithium chloride the I value it will be considering the 100% dissociation, lithium plus the Cl negative I value will be 2. For the MgCl2 it's gonna be Mg 2 positive plus the 2 Cl negative. So 3 it will be there. So among these two, the MgCl2 it is gonna have the more increase in the boiling point it will be there. Okay, so I and the Kb value it's gonna be highest for the magnesium chloride in the presence of in the ethanol solvent. So the correct answer will be the option D. So both this Kb value and this I value, delta Tb was directly proportional to the I value and delta Tb was directly proportional to the Kb value. These two factors we have taken into the consideration. Okay. Moving upon to the next question you have is this one. It says when a non-volatile solute it is dissolved in a volatile solvent, the depression in the freezing point delta depression in the freezing point delta Tf it is proportional to the molality. Direct relationship it is there. So directly proportional to the molality of the solution. So option B it will be. Next is we have this one. It says which one of the following is not a colligative property. So in the starting only we have said four of the colligative properties we have to study: elevation and boiling point, depression and freezing point, osmotic pressure, and the relative lowering in the vapor pressure. So these four are only there. So depression and freezing point it's there, relative lowering and vapor pressure it's there, polar reflectivity this is not there, and elevation and boiling point this is also there. So C is not the colligative property, so C will be the answer in this case. Next is we have this question. The osmotic pressure of a blood at 37 degrees centigrade is 7.5 bars. The amount of glucose to be used per decimeter cube for an intravenous injection to have the same osmotic pressure as that of the blood is approximately. So pi is equal to your CRT. This is what we want, right? Osmotic pressure has to be kept to be the same. So the value will be the same only, that is of 7.5 bars of it. Now concentration it is in the terms of molarity. So number of the moles of the solute upon the volume of the solution. They are saying per decimeter cube. So we can say 1 decimeter cube they are taking as the volume, right? Now the R value it is 0.083 decimeter cube bar per mole per Kelvin, per mole per Kelvin per mole of it. And the temperature it will be your 310 Kelvins of it, right? So with this Kelvin, this per Kelvin will get cancelled out. This bar and this bar term will get cancelled out, and this per decimeter cube and decimeter cube we will be cancelling it out. So we can find from here the number of the moles firstly, and then we can find the amount also. Okay, so we will be getting the n value as 7.5 divided by 0.083 into the 310. So this is in the moles we will be getting it. So weight is we have to find it as in the grams. So glucose, the amount of glucose it is being asked. So the molar mass of the glucose. So the mass of the glucose, it will be multiply it with the molar mass of it. So 7.5 upon the 0.083 into 310 into the 180 grams per mole of it. So with this per mole, this mole term, it will be get cancelled out. Finally, we will be getting it in the grams. So the mass after we solving all of this, we will be getting it as 52.5 grams of it. So the correct answer will be the option A in this case. Okay. Next is this question. It says, consider the following statements. The first statement we have is meats are preserved in the salts. It's true statement, that is meats to prevent it. It's preserved in the salts. The reason for that is same the statement 2 we are having is the cells of the bacteria, they lose the water by the osmosis to the hypertonic solution and they eventually die. It is the true statement. So suppose this is the piece of the meat we are having it, not good one. Suppose this is roughly a piece of the meat you are having it, and you preserve it into the salt. So over it you place the salt molecules. Reason for this is outside solution a lot of the salt we have added. So the solution it will become to be the hypertonic in the nature. Hypertonic in the nature. It's having the more concentration you are having, so more osmotic pressure, so hypertonic. So due to that, what is gonna happen? The water that is present in the meat, it is gonna, because in during the osmosis, water molecules, that is the solvent molecule movement, we observe it from the higher concentration side to the lower concentration side, or reverse of it in the terms of the solute, it is from the less concentration to the more concentration side. So I'm talking in terms of the solvent molecules. Pay attention to that. So more amount of the solvent molecules it is present. Solvent means the water it is present in your meat as compared to your salt. Due to that, what's gonna happen during this hypertonic solution? Due to the hypertonic solution, water from the meat it is gonna come outside. So the meat is gonna shrink in that at that point. So cells are getting being killed at that point. So that is why this prevention of the meat it is possible with the help of the salt. This explanation is also the true over. Okay. So both these statements are the correct and second is the correct explanation. So the correct answer is the option A in this case. Okay. Next one we have is this question. It says which of the following expression it represents the ebullioscopic constant value. Now you might be confused with this term which is your ebullioscopic constant. So it is nothing but your Kb value. This ebullioscopic constant is nothing, it's my Kb value only. So we have seen this relationship for the Kf I told. Now here the direct formula only it is asked. Kb value is R into the Tp square upon the vaporization, delta H of the vaporization into the 1000 into the molar mass of it. Okay, so this is the formula. So you can see it is given to us in the option B. So here the mass it would have been taken in the kgs. That is why this 1000 term is not included over here. Okay, so Pb square is there. In all other terms, if you see Pb is used. Here the boiling point temperature square you have to take. So B will be the correct answer in this. Okay, so this was the last question that was there from this particular topic, which was your solutions and the colligative properties. So I hope all the questions that we have discussed in this chapter are clear to you. If you still have doubt at any of the questions that we have discussed so far, you can ask me in the comment section. I'll surely reply to that. And also for the previous chapters that we have discussed, playlist is there on the channel. You can have a look for that as well. And I'll also provide the link to that in the description. Okay. So next is if you have understood the concept, so make sure you hit the like button for the video and you subscribe to the channel as well because the further chapters also we are going to discuss. Okay, so that is it for this one. We'll be meeting you in the next video now with some new chapter. So thank you so much for watching.